We have now finished with Newton's laws of motion, and we're moving on to Newton's universal gravitational law. Now, when you think about this one, is the expression or the equation that is representing that. It means that every body in the universe attracts every other body, so the masses over their bodies, right, with a force that is directly proportional to the products of their masses and inversely proportional to the square of the distance between the centers. And that is more or less the biggest catch, that one, centers. It must be between the centers. So if you look at an object and you're looking at the Earth is a big thing, right? Now, if that object is over there, usually we have a small object like a rock or a satellite, right? Now, when we have to look at the R that we put in there, remember the R is between the centers, right? And that means it's not the distance above the Earth, right? So usually they give you that one, and then you have to remember that you still have to add the radius of the Earth, and that you get from the information sheet. So in here, remember, mass must be kilograms, R there must be between the centers, and it must be in meters, and then you've got that constant from the information sheet. And I actually think they have 6,67 there. Now, you need to know the difference between mass and weight. Now, mass is just the measurement of how much matter an object is made of, right? Now, how many molecules in my body, right? And that is measured in kilograms, right? And that you can change, right? How can you change mass? Well, you have to go on a diet or practice very hard or eat more, right? You can change your mass only by doing something to change the number of molecules, to change the amount of matter in your body. But weight is the force with which the Earth or whatever planet you are on attract you, and that can change. If you go higher up, obviously R is going to get bigger, and it's inversely proportional to the square of that R. So the further away you go, the less gravity you will experience. So your weight will become less if you go higher up, because then R is bigger and F will automatically be smaller, right? Or if you move to another planet, right? So definitely mass is the one variable that remains constant when you move to another planet or further away. So don't let them confuse you by asking you how the mass is going to change. The mass can only change if they tell you this guy was on a diet. Okay, next up. When you look at the Earth and you look at an object on that Earth, like you on the Earth, right, you can work out the gravitational force with which the Earth attracts you with that equation. But the force with which the Earth attracts you when you're on the surface is actually just your weight. And then you can replace that with m times g. And if you do that, you will see the m can cancel out. And then you end up with an expression, an equation that is not on the information sheet. So you will have to show how you get that one, right? But this is an equation for the gravitational acceleration, right? How fast you fall towards the Earth, right? And that is now independent of the mass, right? The mass cancelled out. So now that gravitational force doesn't have your mass in there, right? So a big elephant and a small mouse, they will be accelerating towards the Earth with the same amount. And if it is the Earth and you are relatively close to the surface, then that will be 9,8 meters per second square. So we can use that. Now let's see how we can manipulate that equation. Now, a lot of times they give you questions like this where they tell you A and B attract each other with a force F. Now, this one's got a mass M and that one's got a mass of 2m, and they attract each other. Now, how big will that attraction be? That one will also be attracted with a force F. Remember, this is Newton 3. If A attracts B, B will attract A with the same force, right? It can only be when you change something that you get a new kind of force. So with this one, they ask, how will the magnitude of that force change when the distance between the centers doubled, right? So they're going to make R double. Now, there are two different methods that you can follow. The first one is you can write the equation down for the F before the change, right? This is the old F before you changed anything, and then rewrite that equation for the situation afterwards, the new one after the change, right? Now, G is a constant, so that didn't change. They said nothing about the masses, so I take it for granted that the masses are the same, right? But the distance between the centers doubled. So instead of R, I'm putting there 2R, right? And now what I want to do is I want to take all the strange numbers out so that I get back to this one, because I know this one is equal to the original F. So at the top, there's nothing strange. At the bottom, I'm taking out that 2, but remember that 2 is squared, so I have 1/4 there, and then I end up with my original equation. So the new force is actually 1/4 of the old force. I like this way. But you can also say, leave out everything that is staying constant, and then that will show you the relationship between F and R. F is directly proportional to 1 over R squared, right? It is inversely proportional to R squared. So that means if R squared doubled, then F would half. So let's see what's happening to R squared. Now R is replaced by 2R, so this whole thing becomes 4R. So this is 4 times R squared. So if R increased with a factor 4, that will mean F decreased with a factor 4, right? Inversely proportional to R squared. So if R squared increased with factor 4, F is going to decrease with factor 4. So the new force will be 1/4 of the old force. Right, so there's two different ways to approach this. Now let's move on to a few questions. Now first, I'm going to ask you, an object experiences a gravitational force with magnitude F on the surface of the Earth. And now I ask you, determine the magnitude of the gravitational force the object will experience at a height. Now remember, height means above the surface, right? Above the surface of the Earth. And they ask you to work out the gravitational force on that height. Now, if you think about this, let's just make a quick drawing. When you've got the Earth, and they are now talking about on Earth, right? So it's over there. So over there you are experiencing force F, right? How would you have calculated that F? You would have calculated that F by saying G m1 m2 over R squared. And remember now, R is the radius of the Earth, because the centers are now R from each other. And now if they tell you you are at a height of the radius of the Earth, that means you are, now height is above the surface, so you are R above. But that means if you want to work out the new force there, that will be G m1 m2 over, and now what is the distance between the centers? You've got 2R between the centers, right? So that actually means you end up with 1/4 of the original force. So over there it's going to experience F over 4, right? Moving on, next question they ask you, how about double the radius, right? Double the radius of the Earth, that means you are at a height from the Earth 2R from the Earth, right? So you are 2R from the Earth. That means if I now calculate the new force, all right, and that is at a height of 2R, this is now going to be G m1 m2 over, now what do we have between the centers? I'm 2R above, but that means I am 3R between the centers, and then I end up with 1/9 of the original one. So there I'll be experiencing F over 9, right? And then the last one, if I am 1, 2, 3 times above the Earth, right? That will mean if I am at a height of 3r, F nu is now going to be g m1 m2 over 4r squared, and I end up with 1/16 of the original force. So over there, it will be F over 16. So the most important thing is to understand the difference between height, right? Height, that is above the surface, and r in your equation, that is from the center. So remember, for r, you have to put in between the centers. Right, moving on to number 2. Now I think it is your turn to start and do number 2, and from 2.2 to 2.7, and then just come back to mark this quickly. Right, let's look at 2.2. So here they tell us an astronaut is 300 kilometers above the surface of the Earth. So you've got the Earth, and then he is 300 kilometers above the surface of the Earth. And now they say if the Earth attracts him with a force of that, calculate the mass of the astronaut. So I don't know the mass of the astronaut. So let's say F equals g m1 m2 over r squared. Now we know the force that's exerted on him, 171. G is a constant, 6,67 times 10 to the minus 11. Now we're looking for the mass of the astronaut, so that is the unknown. And the other mass is obviously the mass of the Earth. And now you have to know that it's on the information sheet. Right, if you go on the information sheet, you will find the radius and the mass of the Earth there. So the mass of the Earth, 5,98 times 10 to the 24th. 5,98 times 10 to the 24. Right, so that goes up there. And then we have to be very careful. What goes down here? Now we need not the distance above, we need between the centers. Right, so we've got that 300 kilometers, which would have been 300,000 meters. And now we have to add that part that is the radius of the Earth. So you have your 300,000 over there, and we have to add, and there they gave it to us, the radius of the Earth, 6,38 times 10 to the 6. 6,38 times 10 to the 6, and remember you need to square down there. Right, and then it is just solving for m. And I hope you all got an m of 80,21 kilograms. Right, so that was for 2.2. Right, let's move on to 2.3. Now they ask us calculate the gravitational acceleration. That's the g, that's not on the information sheet. So I will have to work it out first. Right, I will have to say F is equal to g, let's call it m, big M for the Earth, over r squared. And that is just m times g, because the force between me and the Earth will actually be my weight if I'm on the surface, right? And that is g m r over r squared, and the m's can cancel out, and then I end up with that one. And now I am allowed to use it, right? Now calculate the gravitational acceleration on planet Z, and now they give us the mass and they give us the radius. So this is just substitution, right? So it's 6,67 times 10 to the minus 11. Mass they gave us 3 times 10 to the 23, and the radius they gave us as 2 times 10 to the 6. Right, and remember to square. And there, if you work it out, we end up with 7,00 meters per second square. Right, it's an acceleration, meters per second square. And they ask on planet Z, so this will be towards Z. Right, 2.4. They're asking us what is the gravitational acceleration on a height. Okay, be careful. Height is not radius, right? 3 times the Earth's radius, right? So what I want to do is I want to compare on Earth, right? They're asking us for acceleration. So there I know g is equal to 9,8 meters per second square. And they're now telling us they're going to 1, 2, 3 times the radius, right? So I'm going to start off with this one and say over there, g would have been gm over r squared, right? But now I'm moving over there. I've got a new g, and g is still the same. I'm in the same universe, so I've got the same universal constant. I have the same Earth underneath me, so the mass of the Earth will be the same. But now, remember that r is not the height, but the distance between the centers. So when it was over there, it was r between the centers, but now it is 4r between the centers, and that will just be 1. Remember to square down there, so you end up with 1/16 of the g on Earth, and that will be 1/16 of 9,8, giving you 0,61 meters per second square, right? And that is towards the Earth, right? So towards the Earth. Acceleration is a vector with a direction, right? Next up, they're asking us, John has a mass of 50 kilograms. What is his mass at a height twice the radius of the Earth? Well, if you started doing this question, you are wrong, because remember, we're working with mass. The only way that his mass can change is by going on a diet or doing a lot of exercise, and they told us nothing about this, right? Next up, Mary has a mass of 60 kilograms, and she moves to planet X, and there on planet X, the planet has double the mass of the Earth, okay, twice the mass of the Earth, and double the radius as well. So you'll have 2r as well. Calculate her weight on the planet. Okay, so let's start with her weight on Earth. That would be gm over r squared, or you could have worked that out with m times g. So that will be 60 times 9,8, giving you 588 newtons. So that is her weight on Earth, right? So on Earth it was like this, and now she's moving to planet XX. So what is the force on XX? Now gm, now she didn't change. She was on no diet, right? So her mass is the same, but the new planet has got twice the mass of Earth, and it's got double the radius as well. So at the top, I will take out a 2. At the bottom, I'll take out a 4, and I'll end up with the original one, which used to be 588. So now it is half that 588, which means on this new planet, she will have a 294,00, remember the zeros, Newton, and that will be towards XX, right? So her weight will be towards X, and it is half of what it used to be on Earth. Right, now to the very last one, calculate the gravitational acceleration on planet Z. If I worked out the gravitational acceleration on Earth, that would have been g equals gm over r squared. Remember, you actually have to show how you get that. And that would have been 9,8 meters per second square towards the Earth. Now she's moving to planet Z. Okay, and on Z, g is the same because that's a constant. The mass is now 1/4 of the mass, and the radius is twice that of the Earth. So there you have to do that, and that means you end up with 1/16 of the original acceleration, right? And that means 1/16 of 9,8, and we end up with 0,61 meters per second square, and that will be towards Z.